Good morning, everyone. Today I'm gonna go through the paper, which is called Global Structure from Motion Revisited, aka GLOMAP, from Lin Fei Pan, Daniel Barath, Mark Polyfes, and John Schoenenberg from ATH Zurich and Microsoft. This is a paper that came out like 1 month ago and already has many stars on GitHub, so it's worth knowing a bit more about it. So, first of all, well, the agenda is like I will do a short introduction and we'll go through the literature review of the global structure from motion. Then we talk about the GLOMAP, the technical contribution of the paper, see some results, a demo, and some question at the end. So structure from motion, maybe most of you know already, it is basically getting many images and then the goal is to reconstruct the 3D structure of the environment and also retrieve the camera poses and rotation. So here in the slide, for example, we see the red track are basically the sequence of camera poses with the rotation and position, and these other points here that have color but they seem only black, these are the 3D informations, like a point cloud. So we know GLOMAP. Basically, these authors also built a GLOMAP, and as again we have the images as input, as we can see they are both in both methods. Then we have the correspondence search, which is also common for the two methods, and we will dive into details later on. And then from GLOMAP, we have this incremental reconstruction. So basically, we reconstruct the 3D environment or the 3D structure for every image, and then iteratively add more images and say, okay, what does the new image says about the environment? And so we proceed like that. But this is very time-consuming method. Yeah, so the output is okay, the reconstruction as we saw before, and the new paper GLOMAP, what they say is says, okay, we don't want to do this incremental reconstruction. We will globally estimate the position and the 3D points, but they will have also the same output. And we will focus exactly on this part today to see what's new there. So again, we saw these two main categories. We have the incremental approaches that have superior accuracy and robustness, but they are computationally expensive. The example is GLOMAP. And now we have the global approaches that are more scalable and efficient, but they are less accurate and robust. This an example is Theia, but GLOMAP is another recent example, right? So where is this accuracy gap that is given by the less accurate and robustness? So the main reason is we have a step which is called the translation averaging step. And this is basically the main problem for the accuracy gap, because there are three major challenges in this step. So the relative translation from the two-view geometry can only be estimated up to a scale. And so if the cameras form a skew triangle, the scale are especially prone to noise. And also accurately decomposing the two geometry in rotation and translation components requires prior knowledge of the camera intrinsics. Otherwise, the translation are wrongly estimated or with a very large error. And then, especially with collinear motion patterns such as driving cars, self-driving cars, or videos as well, this is a ill-posed problem basically. So what GLOMAP is doing, they say, no, we are not doing this translation averaging step. We are skipping it altogether. And after the rotation averaging step, we jointly perform camera and 3D points position estimation. And this is exactly the novelty in their work. So now we will just look at what is global structure from motion. Global structure from motion starts as the normal structure from motion, let's say the sequential incremental structure from motion with the correspondence search. So basically we do feature extraction, we search for correspondences between all the images, and we then created this homography, HIJ or FIJ or EIJ, based on the type of motion and intrinsic, if we have intrinsic or not. And then we computed two view geometry with the inlier, and we build this view graph G that is always the input for the next step, the solver. And if we look at GLOMAP, they use the exact same code as COLMAP. So you just need to run the same two lines. So the view graph G does not change. And then basically what happens in global camera pose estimation is that this method aims to estimate all the camera poses, so rotation and position, at once using the view graph G as input. But the main challenge lies in dealing with noise and outliers in this the view graph, and therefore they have to careful model these outliers and noise in order to solve for this optimization problem. And now we arrive at rotation averaging. So these first methods tries to estimate only the rotation of the cameras, and we know that we have like a basically local rotation in the camera frame of reference rotation. So for example, we have R2 and R3 in their own, but we only know the rotation that there is between these two cameras. So we only know R2 and R3, basically R2, 3. And what rotation averaging, well, the output of rotation averaging is having all this relative rotation and being able to compute the, let's say, rotation in world coordinates for each camera, so not relative. And this turns out to, and for example, this is the relation that holds, but it's not always perfect because there are a lot of noise and outliers in the rotation here as well. Therefore, this is theoretically true, but in practice is never really is. There is always with some error. And and so we want to solve this kind of big problem. But given that the rotation is a non-linear, it's like a non-linear optimization because of the inherent nature of the rotations, and therefore we cannot just solve them with a closed form solution. We have to produce a minimization, an iterative. We need to have an iterative solution for this, and most problems states this minimization problem as the distance between this product, which is like we just move this here, and the identity. So we calculate what is the error, and then to some particular distance, for example, the geodesic distance, but many different works use different type of distances. Then we can also control the sensitivity of the distance to make it more or less sensitive to our outliers. And of course, we can use also a robustifier, like example Uber, to make everything more robust in the sense that the algorithm, the iterative algorithm, will converge to the correct local minima, let's say. And so this is rotation average. In the paper, they say that they are gonna use this specific method, but we are gonna see it later on. And then translation averaging is the next step of the rotation averaging. So from these matrices, our homography, for example, we can take out the rotation factor, we can factor out, and then we can only we only have to so we only have to then find the translation that can be found with this formula. But again, due to noise and outliers and the problem, the scale also differences, this task becomes very, very challenging. So the parallel rigidity is also needed. Um, it only also works when the view graph is well connected. So we have many images that see many points on the other cameras, and and then we have also again the problem of the closed collinear motion, which ill poses a problem. And it is only possible if we know the camera intrinsic, otherwise it is impossible to disambiguate the translation from the rest of the intrinsic in the matrix, basically. So this is very tricky. People propose different solution to this, but the main takeaway from here is that GLOMAP says, okay, no, this is we are not doing this altogether. We skip, and we directly do global positioning, and we will see exactly why this works later on. They say that for them, incorporating constraints on the 3D scene structure aids the robustness and accuracy of camera position estimation, right? So they also want to add to their formulation to solve for camera pose estimation 3D points in the space, because they, from literature, it always work best. It always work better when we do so, and therefore this is a good point that they are also taking inspiration from, and we'll see. And then okay, we have global triangulation. So after, yeah, this is the point I meant. So after recovering the cameras, the global 3D structure can be obtained via triangulation, and this is a pretty straightforward step. And then of course, they also have to do global bundle adjustment, and because still they still have to do global bundle adjustment because still the initialization is good, but usually performing global bundle adjustment improves a lot the final results. And I guess we all know that bundle adjustment is basically just like minimizing the projection error from the points that are visualized and the actual points. Then, okay, they go over some hybrid structure for motion, and then they say it doesn't really work um, according to their formulation, and their method even overcomes this. So as technical contribution, we now have an idea of the difference and where the difference is in between GLOMAP and GLOMAP. And now we're going to focus exactly on their technical contribution. So we are going to focus on the global estimation part, especially in the rotation averaging. So in the first part, they have to construct these tracks, but they have to make particular attention on constructing these tracks because so again, global structure of motion is very, very sensitive to outliers and noise. Therefore, they have to put much more consideration into this inlier feature extraction, let's say. So, for example, they only consider inliers that are so they have to carefully reconstruct these feature tracks, and they only consider the inlier feature correspondence produced by the two-view geometry verification. Then they perform the chirality test to see if the point is real or not. I mean, if it's in front of the camera or behind, so they can also remove these. And also points that or matches that are close to the epipoles or have a small triangulation angle are also removed to avoid singularities, and therefore the optimization process might diverge. And only after filtering all these view graph edges, they can then form these feature tracks and concatenating all the remaining matches. So for who doesn't know what a feature track is basically I see a point which is a particular description of a point in 3D space, and the track is how many or in which images I see this point. So if I see it from image 10 to 55, then we know that it's gonna be this feature track is gonna be in this. It's gonna be on all these images, and then basically you can concatenate all these matches to form like the structure, basically, more or less. And then we go to rotation averaging, and as they said, they basically create their own implementation of this method from 2013 at the efficient and robust large-scale rotation averaging. So I will briefly explain how it works. So we are back at here again. So we have a problem. Well, we have a minimization problem that requires an iterative solution, an iterative algorithm to be solved. And what they do is they make use, of course, of the Lie groups and Lie algebra because it is it is a very handy way to let's say do computation on the rotations in this particular set of geometries. In particular, because there is a one-to-one mapping between rotations from Lie algebra and Lie groups. So what this means is that we can go from the Lie group to Lie algebra by, for example, doing the logarithm or then doing the exponential to go back to the Lie group. And it's easier to do operation in the Lie algebra because a rotation in Lie algebra become linear operation. So here, for example, we have this relative rotation ij1, ijk to ijk, and we want the output as to be like R global, R1 to Rn. So we initialize R global to a random initial guess, and then we perform these steps until a threshold of it's reached, so an error is minimized, let's say. So first of all, they compute here the residual, let's say, or the error that is from the relative rotation to the random initialized rotation. And so they have some residual there, some delta. And then they map this rotation to the corresponding rotation in the Lie algebra. And then basically by doing so for all the matrices, they can build a linear system which equals the global rotation to the relative rotation, right? And of course, this is also in the Lie algebra. And then they can linearly solve this, which is quite faster and more efficient. This is gonna look like a sparse matrix of identities. A is gonna be, and these are gonna be just a concatenation of this rotation basically. And then they solve this, and then for every k, then they go back for the R global, they go back to the Lie groups by exponentiation, and then they perform this operation in the Lie groups because this is only possible in the Lie group. Then we have the global position. So this is actually the main point that is introduced from this paper. And at this point, we have a very good initialization of all the rotations of the cameras. What we are missing now is the position of the camera and the position of the points. So now we want to jointly recover point and camera position. So we can easily see in this image that we have a set of cameras that are actually randomly positioned in the space, and so is done, and the same is done for the point. And the output, we actually want it to be the position of the camera that changes to the right position, and also the points can change. So also the points basically move. And the way that they do is very interesting because they want to minimize the distance between this black arrow, let's say, and the corresponding gray and dotted arrow. So here we can see that it is actually, let's say, pointing in the correct direction, but the point is, for example, like it's pointing in the correct direction here, but the purple one is not in the correct position. So here is also an iterative process that will move both points as well as camera centers in their right position. But how do they do this? So first of all, one thing that they do different from the other global structure from motion is that they discard completely the relative translation constraints because it is unbounded. So it will cause more problems than actually brings benefits to, to according to this paper. And they optimize, or um, they pose the problem as an optimization or minimization of the points, the camera center, and some distance um, scaling factor d. So in practice, what we have here is VIK is the our black vector, which is the observed direction of the point in space. And then we have this other term, which is the estimated direction of the that point. So for example, this is the observed direction for the yellow point, which is actually the expected direction, let's say, whether this is the actual or the estimated direction of the point now, right? This is before initialization. I mean, this is at the very beginning. So what they want is they want to minimize the distance between these two, not these two, but they want to minimize the distance between the observed and estimated direction for each point in each camera. So this becomes like a very big optimization problem. And that is actually what we see here. We have a situation in which the distance, so the angular distance is minimized for each point in the space and for each camera in the space as well. For example, here we see the estimated direction d and the observed direction. So we also have this scale factor because we want to compare the scale version of this. We want to compare the scale of this, and actually we hope to get a optimum this and then kind of optimize. So as we said, all the points and cameras centers are initialized by a uniform distribution in the range of -1 to 1, and the normalization factor is initialized as 1. So this is the initialization. And they discarded the translation error because it is unbounded. So there could be a big error. So it like could be potentially infinite. But this error here we see from the rays, it's only a distance between two vectors, and it is strictly bounded to the range 0, 1 as they pose. So this helps the optimization process to converge more robustly, basically. And yes, the sigma is basically the distance between the two vectors, so the angle between the two vectors, basically. And so this is one of the advantages of this reprojection error that they use. And the second is that the objective function, as they experimentally showed, converges reliable even with random initialization due to its bilinear form. That it's actually sometimes not true because I found some, let's say, counterexamples, but yeah, that I will show later. So, okay, we have the two key advantages here. Is that these methods can be applicable with unknown camera intrinsic or even inaccurate, because poor camera intrinsic will only bias the estimation of individual cameras and not like bias the whole process, let's say, because of exactly this. Um, and then we can apply GLOMAP or in collinear motion scenarios, which were known to be a degenerate case for the translation averaging, but we don't do that, so it's fine for now, let's say. And then we have the bundle adjustment, still this classical step that has to be done. So this initial, let's say, step provides us a robust estimation of camera poses and points in space, but it's limited in accuracy. Therefore, several rounds of global bundle adjustments are performed using Levenberg, Marquardt, and the Huber laws. And in a special way, let's say first camera rotation are fixed and then jointly optimized with intrinsic endpoints. And this is very important for sequential data. This goes on until some ratio of filter tracks falls below 0.1, so most of the tracks are, let's say, accepted. And yes, now we have the structure refinement. Sometimes they also tackle, let's say, image from the internet, and since they start from this, let's say, cube of -1 and 1, like point cloud, it's in a cube, but maybe some of these places are like just separate, and so they don't have much in common. So they want to see if they have to like cluster this camera, and how do they do that. So they start from the graph, the initial graph, and they remove all the pairs of images from the edges that have fewer than 5 visible points for each image. And then they calculate the median of points for the remaining pairs and set as t. Then they basically only use strongly connected components or images that have more than t counts, so they cannot cluster these and only use the cluster, like create a cluster only if it is connected with more than t counts. And so they start with many clusters, let's say, and then they try to merge these clusters. Um, they try to merge two strong connected cluster if there are at least two edges with more than 0.75 t, so this threshold. And they keep doing this until there is no more edges that can be found that satisfy this constraint. And if there are still, let's say, disconnected edges or cluster, then every one is a different reconstruction, let's say. So that's what they do. As a result, this is a very interesting part. So let's say they do their own experiment on ATH 3D SLAM, where the dataset is quite challenging. They are okay, sequential data, dynamic object, and drastic elimination changes. And well, they said how they like evaluated and compared to the ground truth and so forth. Here we can see that most of the results and metrics show that GLOMAP is actually superior to all the rest. And beside in the time here, we can see that OpenMVG, also a global structure from motion, is also leading and data as well. But then GLOMAP is also like in the same order of magnitude at the same time. But what we notice is that COLMAP is actually not in the same order of magnitude. Most of the time is like here is probably 10x longer than any of other of these methods, which are actually global estimation, global structure for motion, basically. So I think this is one of the important takeaways from here as well. Then they also show these are the results from still ATH. Here also GLOMAP, it's kind of leader in the accuracy. And then here they basically under area of under the curve is with 1 degree is like the error in the angles with the ground truth. Um, and still here we see that now the gap is closing with the coil map because there are less images. And I also did with the like DSLR images on such kind of data set, and here also the images are not not it's not too many, let's say, so it's still manageable. And here again we see GLOMAP always on the lead, um, even though most time the difference is not outstanding. Like GLOMAP is always following up very close, maybe just a couple of points difference, but still GLOMAP in these results, in this baseline, let's say it shines, I would say. Here, given the low number of images, for example, the GLOMAP and COLMAP time is actually very, very similar, because like GLOMAP in general also has to do bundle adjustment. So if it has to do bundle adjustment and a similar number of time as COLMAP, then the speed up is not um, as much as we could hope for. But of course, when the dataset grows bigger and Colma will perform much many more times the bundle adjustment than GLOMAP, and therefore that is when we see actually a good speed up. They also show the results on the Lamara, this new dataset, which has a lot of images. We can see here like a lot of points taken from this IR ad set, and here, okay, they show still GLOMAP. It's okay, and also here we see the different like results, and of course, for example, some even fail. Of course, we have a small accuracy for Theia, but it was also the fastest. GLOMAP is second in, and COLMAP is the longest one because of how many images there are in this dataset, let's say. So this is also to keep in mind. We also did the other results here. So yeah, even here, for example, here is very, very close also to Colmap. It's very, very close to Colmap, yes. And then they also show results to MIP 360, where still GLOMAP and COLMAP are very close, and the speed up is there, but not not as much as we could hope for, because exactly the number of images are still, let's say, manageable. I don't remember which one, but in some of them, like the ground truth was COLMAP, and so effectively I don't know how they can like compare these things. But the result on IMC it's built by Colmap, so yeah, they give a bit more, let's say, space to the degree of error, but still. So of course this method has also limitation. They say that it has satisfying performance, which actually reflects what we have seen in the results. But there remain still some failure cases. Some of them are in these results, like a failure of rotation averaging due to symmetric structure, for example, the exhibition all in table 3, basically. Let me see here if you can see the exhibition hall. We can see here GLOMAP is very, very low, and I don't remember if it has like some mirrors or it is exactly like the same type of structure is on the right and on the left, so kind of gets confused with the rotation averaging and not rotation average, but you get confused with the point optimization step, let's say, on the symmetric structures. And And of course, they also rely on the traditional correspondence search. Therefore, if there are incorrectly estimated to view geometries, that basically leads to a catastrophic failures because every error that is done at the beginning kind of amplifies all the errors down the line. So this is also something that, nevertheless, in my experience, it wasn't all these amazing. Like it has a lot of good use cases, but I experience a lot of failure cases even here, and sometimes I'm quite um, let's say impressed by the results they got and that they diverge, let's say, from what I've experiencing. But on the other hand, that makes sense of what they say because like the reconstruction I'm doing are in places where there are similar places. There is still a lot of um, difficult images. So if the traditional correspondence fails, then everything down the line also fails. So it's still aligned to their findings. And yeah, so I want to briefly conclude and give like the main takeaways of this paper. One the thing that they do, the clever thing that they do is that they say, okay, translation is not working best. We take away and we take it away and we replace it with a more robust method that uses this raise um, difference to minimize and get the solution. And this is a single uh, step that jointly optimizes for poses and points. So they replace this, and then they show that the results are on par or superior to GLOMAP. One thing that stood out, I would say, is that they have random initialization. So you can make it, of course, deterministic by not using a random initial. I mean, knowing always what the random initialization would be. But yeah, sometimes this is tricky because you don't know anymore where the error come from, let's say. And then, I mean, it's 10 to even 100 times faster for some particular use case scenario. And of course, the code is open source, and I would really encourage you to try it out and see if you get similar results as well. One thing I would love to add is this global structure from motion. I think they are getting more popular now because GLOMAP has been the de facto standard for so long. But with GLOMAP and even at the same time, actually a new paper dropped that was master SFM, and they also try to do global pose estimation structure from motion, taking a very different approach with transformers and so with transformers as well. They also show their comparison with GLOMAP, A0, and some other differentiable methods. They don't show any comparison with GLOMAP because it wasn't out yet, but even here the results are quite good, I would say. I tried it, but I wasn't very satisfied with this method as well. But it gives quite a dense point cloud, and I think we should kind of consider these new methods coming out because they are very, very interesting. And there is still, I think there is quite some movement here. And yeah, I can take any question now, and I still have some example of my own experiences to show, and then a demo. So I don't know how you want to proceed, but so for example, we see like these are some experiments that I was doing. GLOMAP kind of gets the overall structure very well, but of course it kind of fails in doing the loop closure. And there are different explanation we kind of got. One was the drift around the curve, or the drift in a very linear motion. That is actually what we saw here in the paper. But still, the overall structure is there. GLOMAP actually fails quite badly on this, and I didn't really figure it out why, but probably because of the large number of images and difficult maybe environment. So I mean, the GLOMAP is not the replacement for everything, and as of now, for example, I'm still using COLMAP as it is kind of more reliable as well. Even here we see another example. We see that COLMAP here kind of breaks um, because of similar structure probably in our buildings here, uh, but still most of it is quite correct. On the other side, GLOMAP gets some of it, but then drifts away and then produces images just garbage, I would say. Then another quite funny example is GLOMAP. These are all the same inputs, just different runs, and sometimes it gets it very accurate, some other times as well, but sometimes it just do not converge to the correct minima, let's say. And because of this, I didn't understand at first, but then I quite understood, which is because of the like random initialization. So at this point, the only thing that I could come up with is that these random initialization are not really always leading to the same minima, um, even if the paper states so. But of course, GLOMAP is still very good. We have failure cases in COLMAP, for example, in this linear motion, right? And with COLMAP, again, it was probably ill-posed problem, and because of the kind of difficulty of this image, we couldn't even get it correct on COLMAP. But on GLOMAP, we actually got a pretty decent result as input, as output. So yeah, this is my experience. Now I can show you a small demo. So yeah, I don't know why it takes just a while, but so we can see. So here is the initialization, right? This is the rerun software, rerun viewer. It's quite amazing. I took a while to realize how to use it, but it's really good. So this is the random initialization of the points from -1 to 1, I would say, and so on and so forth, like in 3D. And now we have the rotation, like the rotated images all around, right? So they have their own rotation already. So this is the result of rotation average. And then now we have the step of optimization. So this is what the images do, right? So again, we start from the rotation initialization. The points are like stars around, and then basically the images start to kind of get optimized with the optimization formula or that we saw before, and then at some point they quite reach some agreement. So we can see that there is already some structure around. We can see actually the points got distributed quite good. And then I think at some point here we see quite some jumps. So now here is still optimizing, I would say. Right. And then, yeah, I think we saw these jumps are the results of bundle adjustment. So each jump is bundle adjusted, and then see, I think there was this image here which because of the bundle adjustment got away, but then it came also back because of the yeah. So this is the final reconstruction that we would get from GLOMAP.